Welcome to Signals and Systems. Throughout this lecture, I'd like to request you to pause the video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. In some of the lectures, we'll play around with some of the signal processing ideas in MATLAB, so I'm assuming that you already have some level of exposure to MATLAB. In this lecture, we're going to talk about template signals. We call this signal models because other signal can be expressed in terms of these models. Signal models simplify various aspects of signals and systems. The models we're going to talk about are step function, impulse function, ramp function, rectangular function or rectangular pulse, and sinusoidal signal. The step function or unit step function u of t is defined using this mathematical expression. It's 1 when t is greater than 0, and then it's 0 when t less than 0, and it's undefined at t equals to 0. So the unit step function u of t is 0 for negative values of t and 1 for positive values of t. So is a step function analog or digital? Continuous time or discrete time? Causal or anti-causal or non-causal? Periodic or aperiodic? So just think about it and then we'll match our answers. Okay, the step function is digital because it only has two possible values, 0 and 1. It's definitely continuous time. It's defined for any value of t. It's a causal signal. It only exists on the right side of the y-axis. It's an aperiodic signal. That is, it's not a periodic signal because it doesn't have a pattern that gets repeated every t seconds. So let's say you have a signal x of t. If you multiply it by the step function, you end up with the causal portion of x of t. That is the portion that exists on the right side of the y-axis. Let's say, an important application of step function is that you can express a time-limited signal using a linear combination of step functions. So a signal that is time limited between t equals to a and t equals to b can be expressed by the difference of two delayed step functions, u of t minus a, u of t minus b. So let's say we have a signal that exists only between 1 to 2 seconds. So the signal is time limited between 1 to 2 seconds. How do we express this signal as a linear combination of step functions? So in order to do that, we basically have shown each of the steps here. So in the first panel here, the red signal here basically is the unit step function that starts from 0, and for t greater than 0 it's 1, and for t less than 0 it's 0. So our signal basically exists from t equal to 1 and 2 seconds, which means we need a one step function which is u of t minus 1 and another delayed step function which is u of t minus 2. So I've just delayed the red step function here to obtain the green step function, and I've delayed the red step function for 2 seconds to obtain the blue step function in the third panel here. Now if you subtract the signal in panel 3, the blue signal, from the signal in panel 2, the green signal, we end up with the signal in panel 4, the black step signal here, that exists between 1 to 2 seconds. Now we can just multiply our signal x of t, which exists only between 1 to 2 seconds, with the function u of t minus 1 minus u of t minus 2 to express x of t in terms of combinations of step functions. Okay, now here's an example problem. Now please pause this video and try to express this signal using a combination or a linear combination of step functions. So please pause this video. So hopefully you've been able to solve this. So this signal is time limited from 2 seconds to 4 seconds. So if we get a step function u of t minus 2 and another step function u of t minus 4 and subtract u of t minus 2 from, subtract u of t minus 4 from u of t minus 2, we end up with this time limited signal that exists between 2 to 4 seconds. Okay, now please pause this video again and then we'll match our answers. Okay, so hopefully you've been able to solve this problem. So we see that this signal is equal to 2. So at first what we're going to do is we're going to convert this signal as a mathematical function or equation. So we can see that when for time minus 0.15 second to 0 second, the signal's value is 2. So that's why we're added here. And for 0 to 3 second interval, the signal obeys 2 e to the power minus t by 2. This equation, so we have this equation here from 0 to 3, and otherwise it's 0. So this function 2, which is valid for minus 1.5 to 0 second, can be expressed using an advanced step function minus another step function times 2. And this can be expressed as 2 to the power minus 2t u of t minus 2 to the power minus t by 2 u of t minus 3. So basically the difference of step function that starts from 0 and another one that starts from 3. And what we do next is we just sum these two equations to obtain the final expression of x of t with respect to u of t, the step function. Okay, now we're trying to do the inverse thing here. We have a function that is expressed with respect to a linear combination, a combination of step function. Now we're trying to draw the signal here. So please pause this video and try to solve this problem, and then we'll match our answers. So hopefully you've been able to solve this problem. So we see that you have 3 step functions here, 1, 2, 3. So we'll have probably 4 limits. One for t less than 1, another is t equal to 1 to 2, another is t equal to 2 to 4, another is greater than 4. So for t less than 0, none of these step functions here are 1. All of them are 0. That's why the output is also 0. X of t is also 0. When t is greater than 1 but less than 2, this step function gives 1, this one gives 0, and this one gives 0. That's why x of t is equal to t minus 1. When t is greater than 2 but less than 4, this step function gives 1, and this step function also gives 1. So we have t minus 1 from this step function, and from this we have minus t minus 2. So if we do some algebra, we end up with 1. And lastly, the last interval, t greater than 4, where all these step functions give 1, we have t minus 1 minus t minus 2 minus 1 to obtain 0 here. Okay, so please pause the video and try to generate these plots in MATLAB, and then we'll match our answers. So please pause this video. Okay, so again, I have selected the sampling rate as 500 Hertz and set the time axis from minus 5 second to 5 second, and basically I've used a logical operation here to set all the tvec values greater than 0 to find the indices of all the tvec values greater than 0, and only for those values I set the step function equal to 1, otherwise it's 0. And then I just plot it, and to introduce a delay, so I've basically selected two variables, delay 1 and delay 2. So this is for u of t minus 1, and this is for u of t minus 2. And I use the exact same logical expression to compute to generate the delayed unit step functions. And these are just plotting commands, as shown in the earlier lectures. So if we run this, we get our plot that I just shown earlier. Okay, now please pause this video and try to solve this problem, and then we'll match our answers. Okay, so hopefully you've been able to solve this problem. Again, here is another problem for your practice. Please pause this video and describe the signal using step functions, and then we'll match your answers. Okay, so hopefully you've been able to solve this problem. So the unit impulse function, or delta function, or Dirac delta function, is equal to 0 everywhere except t equals to 0, where it is undefined. So how then do we get an intuition of what this thing is? So the unit impulse, or delta function, can be considered as a rectangular pulse, as shown in figure B, with a width that is infinitesimally small and a height that is infinitesimally large, that is infinitely large, such that the area under the curve is 1. That's why from minus infinity to plus infinity, if you compute the area under the curve of the delta function, you get 1. The definition of delta function is that it's equal to 0 for t not equals to 0, and it tends to infinity at del of 0. Also note that del t is an even function, so if you flip it or perform time reversal with respect to the y-axis, the signal remains the same. So since del t is 0 everywhere except for t equal to 0, where it becomes infinity, it is represented by the spear-like symbol shown in figure A. So now we're going to talk about 3 properties of delta function: sampling property, sifting property, and scaling property. So let's first talk about the sampling property of the delta function. So let us now consider what happens when we multiply the delta function del of t by a function phi of t that is known to be continuous at t equals to 0. So since delta function has a non-zero value only at t equals to 0, and the value of phi of t at t equals to 0 is phi of 0, we obtain phi of t times del of t is equal to phi of 0 times del of t. Because for all the other time points, del of t is 0, so 0 times signal amplitude is 0. So they don't count. So if we consider a delayed delta function, we get the general equation of the sampling property as shown below. Del of t phi of t minus capital T is equal to phi of capital T del of t, where capital T is the delay. Okay, the sifting property involves minus infinity to infinity phi of t del of t dt is equal to phi of 0. So the sifting property can be proven using the sampling property. So minus infinity to infinity phi of t del t is equal to minus infinity to infinity phi of 0 del of t. And phi of 0 is a constant. It can be taken out of the integration, and we end up with this thing, minus infinity to infinity del t dt. By definition of delta function, this integral is equal to 1. That is why the value of on the left side of this equation is phi of 0. So this result means that the area under the product of a function, phi of t, with an impulse del of t, is equal to the value of the function at the instant at which the unit impulse is located. So phi of 0 means the delta function is located at t equals to 0, and the integration means area under curve. So considering a delayed impulse function, we get the general equation of sifting. It looks something like this. So this is basically saying that if the t naught here, that is the location of the delta function, falls within the limits of integration, that is t1 and t2, the output is vt naught, and if it is outside the limit of integration, then it's 0. Okay, so the last property of delta function that we're trying to discuss is the scaling property. So scaling property says that if instead del of t, what happens if we have a scaled version of time? So del of at plus b is equal to 1 by mod a plus del of t plus b by a. So that's how you sort of get the scaling factor out of the time and bring it in front of the delta function. Okay, now having the three properties of delta function in mind, please pause this video and try to solve this problem, and then we'll match our answers. So hopefully you've been able to solve this problem. So the delta function is located at t equals to 1 here. 1 is within 0 to 7, which is why we can just set t equals to 1 for this function. For that we get 1 plus 1 equals to 2, and that's our answer. Okay, now please pause this video again and try to solve this problem, and then we'll match our answers. So hopefully you've been able to solve this problem. Again, 10 lies between 0 to infinity, so phi of t here is e to the minus t, and we just apply the sifting property to solve this problem. Okay, here is another example. So this is actually worked out here. So what happens if we integrate the delta function from minus infinity to t? So if you integrate delta function from minus infinity to t, the answer actually depends. It depends on the sign of t. So if t is a negative number, remember that the delta function here, for delta theta, for delta tau, delta function is located at tau equals to 0. And if it's a negative number, 0 is not included in this range. So let's say t is minus 5. Then the limit of integral minus infinity to minus 5 does not contain the impulse function, which means according to sifting property, the output will be 0 for t less than 0. And similarly, if it's greater than 0, it must contain the delta function, which means minus infinity. So the integral includes the delta function and delta function alone, which is why it is equal to 1. So we end up with this. If t is less than 0, we get 0. If t is greater than 0, we get 1. So for t less than 0, the integral limit will not contain the impulse function, and for t greater than 0, the integral limit will in fact contain the impulse function. Wait, this looks familiar. This looks exactly like step function. So we learn from this, when we integrate a delta function, we get a step function. Conversely, we differentiate a step function with respect to time to obtain a delta function. Okay, here's a summary of the properties of delta function. So the first one is the sampling property. The second one is the sifting property. Please don't confuse sampling with sifting. Sifting has an integral with respect to time. Sampling doesn't have that. And this property basically says that if we differentiate a unit step function, we end up having a delta function. And this is the opposite of property 3, where we integrate the delta function to generate the step function. And this property shows that delta function is an even function, that is, it's symmetric with respect to the y-axis, and there is a scaling property of the delta function. Okay, now please pause this video and try to solve this problem in MATLAB, and then we'll match our answers. So please pause this video. So hopefully you've been able to solve this problem. So here I've again defined a sampling rate of 500 Hertz, and I'm looking into minus 5 to 5 seconds. And again, I've generated a delta function using a logical operator here. So this equality operator is only 1 when the time vector is equal to t0, and the t0 is set to 0 here. So using this logical operation, we can generate delta function just like we did for step function. And to implement the delay, we just change t0 equals to 2, so it's 2-second delay. And if we want to advance the impulse or delta function, we just let's say for 3 seconds, then we set t0 equals to -3. So if we run this, we get this plot where you have the impulse function at t equals to 0, and this is a delayed impulse function by 2 seconds, and this is an advanced step function by 3 seconds. Here's the typo, it should be t plus 3, excuse me. Okay, now please pause this video and try to solve this problem, and then we'll match our answers. So hopefully you've been able to solve this problem. We move on to our next signal model, unit ramp function. So the unit ramp function is equals to 0 for t less than 0, just like step function, but for t greater than or equal to 0, it's r of t, the ramp function here, is equal to t. So it's basically a straight line for t greater than or equal to 0. And the slope of the straight line is 1. So now differentiate a ramp function with respect to time and see if you see anything interesting. So please pause the video and try to differentiate a ramp function with respect to time. So please pause this video. Okay, so we should keep in mind that the three singularity functions, step function, delta function, and ramp function, are related by differentiation using these equations. So if you differentiate a ramp function here with respect to time, you obtain a step function, and if you differentiate a step function with respect to time, you get a delta function. And conversely, it can be said that they're also related by integration, because integration is just the reverse operation of differentiation. So if you integrate the delta function, you end up having a step function, and if you integrate the step function with respect to time, you end up having a ramp function. So please test your skills by generating a unit ramp function and its delayed and advanced versions in MATLAB. The next signal model we're going to see is rectangular pulse signal, rectangular pulse function. So the unit rectangular pulse is defined using this equation. So here tau basically indicates the width of the pulse, and you usually have a t minus a in this equation here, where the a indicates the center of the rectangular pulse, but it's not shown here because the rectangular pulse is centered at 0. So it's basically t minus 0 divided by tau. So between minus tau by 2 to tau by 2, the rectangular pulse is 1, otherwise it's 0. So the tau here is basically showing the width of the pulse, and t minus a here shows the center of the rectangular pulse. So now please pause this video and test your skills by generating a rectangular pulse using unit step functions. Okay, so hopefully you've been able to do this. So that's how you generate a rectangular pulse function using unit step function, and the rectangular pulse function results from the operation of a switch, and it is used to extracting part of a signal, just like unit step function. Okay, the last signal model we're going to talk about is also the most important one, the sinusoidal signal. So this is the most important and useful of all standard signal models, and sinusoidal signal usually means sine wave or cosine wave. So the equation basically takes the form x of t is equal to sine omega t, where omega is the angular frequency, and the relationship between angular and linear frequencies, omega is equal to 2 pi f. The sinusoid, sine omega t and cos omega t both are same, because sine and cos are basically related by a phase shift. So alternatively, sinusoidal signal can also be expressed by the application of Euler's identity. E to the power j theta is equal to cos theta plus j sine theta. So e to the j omega t gives us cos omega t plus j sine omega t, where omega is the frequency of the sinusoid. So this is also an alternative expression, exponential function. Using exponential function here, we can express sinusoids. So these are two alternative ways to express sinusoid signals. So you need three parameters to completely define a sinusoid: amplitude, frequency, and phase. So for an identity card of Mr. Sinusoid, you need three parameters: amplitude, frequency, and phase. The A here is the amplitude, F here is the frequency. It could also be omega, which is the angular frequency, F here is the linear frequency, and theta here is the phase. So a sinusoid is a periodic signal and goes from positive infinity to negative infinity. Okay, so now we're going to test our skills by generating sinusoidal signals in MATLAB. So please pause this video and try to do this, and then we'll match our answers. So please pause this video. Okay, again, we've selected the sampling rate at 500 Hertz, and we're going to look into the signal from -5 second to +5 second. And our first sinusoid has an amplitude of 3, our second sinusoid has an amplitude of 2, and a third sinusoid has an amplitude of 1. So, and the frequency here, the linear frequency here, is 1 Hertz. This is the 2 Hertz component, and this is the 3 Hertz component. So I haven't added any phase shift here. If you want to add a phase shift, let's say 45 degrees, you just add pi by 4 here. So 45 degree in radian is pi by 4. The signal here, I've generated the signal by summing these three sinusoidal components. So that's how we generate a sinusoidal signal with 1 Hertz, 2 Hertz, and 3 Hertz frequency components. And I've used the regular plotting functions to plot the sinusoids. So if we run this, we have something like this. So this is the 1 Hertz component, this is the 2 Hertz component, and this is the 3 Hertz component. The amplitudes are also decreasing, and if you sum them, you end up with a periodic signal. And this is the sum of the three sinusoids. So this concludes our lecture on signal models. If you have any questions, please feel free to drop a comment. And thank you for your time.